object. So this is the overall model that we want to use. So for each position in our corpus, our body of text, we want to predict context words within a window of fixed size M given the center word WJ. And we want to become good at doing that. So we want to give high probability to words that occur in the context. And so what we're going to do is we're going to work out what's formally the data likelihood as to how good a job we do at predicting words in the context of other words. And so formally that likelihood is going to be defined in terms of our word vectors, so they're the parameters of our model, and it's going to be calculated as taking the product of using each word as the center word and then the product of each word in a window around it of the probability of predicting that context word in the center word. And so to learn this model, we're going to have an objective function, sometimes also called a cost or a loss, that we want to optimize. And essentially what we want to do is we want to maximize the likelihood of the context we see around center words. But following standard practice, we slightly fiddle that because rather than dealing with products, it's easier to deal with sums. And so we work with log likelihood. And once we take log likelihood, all of our products turn into sums. We also work with the average log likelihood. So we've got and essentially what we want to do is we want to maximize the likelihood of the context we see around.
So I think this is something we had discussed before as well. I think during the multiplied video that we were doing, right? The negative log likelihood means log. So log converts those multiplications into additions, and usually the graph of log looks something like this. So yeah, usually this is how the value of log or the function of log looks like. It is like this sort of a value. So only reason of doing this as he told, right, because it's a multiplication that is coming in here to convert it into addition, which is much more simpler to differentiate and everything, because each can be handled, each element in the sum can be handled differently. And again, the negative log likelihood, because it will flip if you subtract multiplied by -1, right? The graph will become something like this. Here we can see this. So this is somewhat how a negative log will look like. And this is how it will look like, and we usually try to crush the values in this range whenever we will be calculating the errors and everything, right? So that if it is much more closer to 1, it will have a less value of fx. If it is closer to 0, it will have much higher value of fx. So in a way that tells us that how far it is from 1. If it is close to 1, means there is much more likelihood error should be less, or loss is much less. If it is much more closer to 0, the loss is much more. But anyway, we'll go through it and see when we are trying to implement it in Python and everything, right, how it is happening and everything. So all those sort of
center words, but following standard practice, we slightly fiddle that because rather than dealing with products, it's easier to deal with sums. And so we work with log likelihood. And once we take log likelihood, all of our products turn into sums. We also work with the average log likelihood. So we've got a 1 on t term here for the number of words in the corpus. And finally, for no particular reason, we like to minimize our objective function rather than maximizing it. So we stick a minus sign in there. And so then by minimizing this objective function, j of theta, that comes as maximizing our predictive accuracy. Okay. So that's the setup, but we still haven't made any progress in how do we calculate the probability of a word occurring in the context given the center word. And so the way we're actually going to do that is we have vector representations for each word, and we're going to work out the probability simply in terms of the word vectors. Now, at this point, there's a little technical point. We're actually going to give to each word 2 word vectors, one word vector for when it's used as the center word and a different word vector when it's used as a context word. This is done because it just simplifies the math and the optimization. So it seems a little bit ugly, but actually makes building word vectors a lot easier, and it really we can come back to that and discuss it later, but that's what it is. And so then once we have these word vectors, the equation that we're going to use for giving the probability of a context word appearing given the center word is that we're going to calculate it using the expression in the middle bottom of my slide. So let's sort of pull that apart just a little bit more. So what we have here with this expression is, so for a particular center word and a particular context word O, we're going to look up the vector representation of each word. So they're U of O and V of C. And so then we're simply going to take the dot product of those 2 vectors. So dot product is a natural measure for similarity between words, because in any particular dimension, positive, you'll get something. A component that adds to the dot product sum. If both are negative, it'll add a lot to the dot product sum. If one's positive and one's negative, it'll subtract from the similarity measure. If both of them are 0, it won't change the similarity. So it sort of seems a sort of plausible idea to just take a dot product and thinking, well, if 2 words have a larger dot product, that means they're more similar. And so then after that, we're sort of really doing nothing more than, okay, we want to use dot products to represent word similarity, and now let's do the dumbest thing that we know how to turn this into a probability distribution. Well, what do we do? Well, firstly, taking a dot product of 2 vectors, that might come out as positive or negative, but, well, if we want to have probabilities, we can't have negative probabilities. So a simple way to avoid negative probabilities is to exponentiate them, because then we know everything is positive. And so then we are always getting a positive number in the numerator, but for probabilities, we also want to have the numbers add up to 1, so we have a probability distribution. So we're just normalizing in the obvious way, where we divide through by the sum of the numerator quantity for each different word in the vocabulary, and so then necessarily that gives us a probability distribution. So all the rest of that I was just talking through, what we're using there is what's called the softmax function. So the softmax function will take any Rn vector and turn it into things between 0 to 1. And so we can take numbers and put them through the softmax and turn them into a probability distribution. Right, so the name comes from the fact that it's sort of like a max. So because of the fact that we exponentiate, that really emphasizes the big contents in the different dimensions of calculating similarity. So most of the probability goes to the most similar things. And it's called soft because, well, it doesn't do that absolutely. It'll still give some probability to everything that's in the slightest bit similar. I mean, on the other hand, it's a slightly weird name because, max normally takes a set of things and just returns 1, the biggest of them, whereas the softmax is taking a set of numbers and is scaling them, but is returning the whole probability distribution. Okay, so now we have all the pieces of our model. And so how do we our word vectors? Well, the idea of what we want to do is we want to fiddle our word vectors in such a way that we minimize our loss, i.e. that we maximize the probability of the words that we actually saw in the context of the center word. And so the theta represents all of our model parameters in one very long vector.
So don't worry, we'll go through one by one how we do all of this in Python. That's my intention. So anyway, just let's go through it.
So for our model here, the only parameters are our word vectors. So we have for each word 2 vectors, its context vector and its center vector, and each of those is a d-dimensional vector where d might be 300, and we have v many words. So we end up with this big, huge vector, which is 2dv long, which if you have a 500,000 vocab times the 300-dimensional vector time, it's more math than I can do in my head, but it's got
So it's making 2 vectors for means 2 vectors. One is the context vector that he told, and one is the actual word vector. And how many number of that d parameters, right? How big you want to represent a word means how many features. So for an person, right, say it has 5 personality traits if you define, right, so it can be defined across say 5 features. He's extrovert or not, he's shy or not, or something like that. I'm just taking an example. So a human being can, if those 5 features, if we can take it and if we can rate it across 100, that defines an individual like that, right? For any word, right, by how many features we want to represent a word, by 10 features, 2 features, 3 features, by how many. So that's one decision that we need to make here as well. But so d-dimensional vectors is just shows that to represent a word like he, let's say he, how many different features we want to use means if the value of those features are 10, 12, 13, 14, just like I'm taking an example, then it represents a he. In that way, every word will be represented with the numbers for those features and everything. So if you are getting confused, right, just hold on. We'll go through this.
Millions and millions of parameters. So we've got millions and millions of parameters, and we somehow want to fiddle them all to maximize the prediction of context words. And so the way we're going to do that then is we use calculus. So what we want to do is take that math that we've seen previously and say, well, with this objective function, we can work out derivatives. And so we can work out where the gradient is, so how we can walk downhill to minimize loss. So we're at some point and we can figure out what is downhill, and we can then progressively walk downhill and improve our model. And so what our job is going to be is to compute all of those vector gradients. Okay. So at this point, I then want to kind of show a little bit more as to how we can actually do that. And a couple more slides here, but maybe I'll just try and jigger things again and move to my interactive whiteboard. What we wanted to do, right, so we had our overall J theta that we were wanting to minimize our average neg log likelihood. So that was the -1 on t of the sum of t equals 1 to big T, which was our text length. And then we were going through the words in each context. So we were doing J between M words.
So 1 to t if we are going for each of the words, and for each of the words we are looking into its context. Okay, means something like if here, right, if say t is equal to 1 2 3 4 5. Okay, so if t is equal to 5, because we are going from 1, we're going first take Stanford, then this, then this, then this, and this. So when we reach this t equal to 1 2 3 4 5, when we reach t equal to 5, right, we are going through the context
Words on each side.
minus m to m, say -2. m is 2 we are taking, so it will take minus 2 is NLP, and width and plus 2 will be, or plus m will be learning. Let's take this is with learning itself, and then winter. Okay, so 2 words after deep, 2 words before deep. Okay, and that is what this, and we'll calculate the probability of seeing width given that deep is in here. That is when for t equal to 5. So same way we'll do for say this and as well. So and we'll take into and this hyphen of, let's take that is a word, right? So when t is equal to some value 1 2 3 4 5 6 7 8 9 10, so t equal to 10, and we are paying so when t equal to 10 right here, uh, we will take plus m will be into plus 2, that is will be this and this, and minus m will be words and vectors, and we will calculate what is the probability of seeing intro given and is there, what is the probability of seeing vectors given and is there, like that we'll calculate 4 probabilities.
Accept itself. And then what we wanted to do was in the side there, we were then working out the log probability.
J not equal to 0 means we'll not calculate what is the probability of seeing and given and is there, because obviously that will be 1. That doesn't make any sense as well.
Of the context word at that position, given the word that's in the center position T. And so then we converted that into our word vectors by saying that the probability of O given C is going to be expressed as the this softmax of the dot product. Okay, and so now what we want to do is work out the gradient, the direction of downhill for this loss gen. And so the way we're doing that is we're working out the partial derivative of this expression with respect to every parameter in the model, and all the parameters in the model are the components, the dimensions of the word vectors of every word. And so we have the center word vectors and the outside word vectors. So here, I'm just going to do the center word vectors. But on a future homework, assignment 2, the outside word vectors will show up, and they're kind of similar. So what we're doing is we're working out the partial derivative with respect to our center word vector, which is, maybe a 300-dimensional word vector, of this probability of O given C, and since we're using log probabilities of the log of this probability of O given C, of this X of U of O T V C over, my writing will get worse and worse, sorry. I've already made a mistake, haven't I? The sum of W equals 1 to the vocabulary of the X of U, W, T, V, C. Okay, well,
So if you remember in the micrograd example that we are doing, right, for the loss we see how other variables in the whole of the chain, right, that impact the d loss by d, all the variables that we have seen. So that's how we try to back propagate and change the value. So it's somewhat like that itself. So the way we have defined loss is log of this probability here, and we are trying to see how this loss is getting impacted because of the input vector. If it sounds a bit confusing, right, we'll go through again, means when we'll try to implement this, right, we'll take it a bit step by step and see how it is being done.
well, at this point, things start off pretty easy. So what we have here is something that's log of A over B. So that's easy. We can turn this into log A minus log B. But before I go further, I'll just make a comment at this point. So at this point, my audience divides in two, right? There are some people in the audience for which maybe a lot of people in the audience, this is really elementary math. I've seen this a million times before, and he isn't even explaining it very well. And if you're in that group, well, feel free to look at your email or the newspaper or whatever else is best suited to you. But I think there are also other people in the class who, the last time I saw calculus was when I was in high school. Most of deep learning, it's really just seems like magic, that it's not really magic. It's really just doing math. And one of the things that we hope is that you do actually understand this math that's being done. So I'll keep along and do a bit more of it. Okay, so then what we have is sort of use this way of writing the log. And so then we can say of VC of GVC minus of the log of W equals 1 to V. Okay, so at that point, I have my numerator here, and the first part is the numerator part. So the numerator part is really, really easy. So we have here that log and x are just inverses of each other, so they just go away. So that becomes the derivative with respect to VC of just what's left behind, which is u. The thing to be aware of is, we're still doing this multivariate calculus. So what we have here is
usually this, right? So I'm not sure if you're aware of this or not. If I can find that, right? I can, or you can search it around. Same. So usually, right, if ln or log of e, usually ln is log of e. So if e is in the base here, right, and e to the power m we are doing, so m comes here and this becomes 1. So whatever is the power that comes out. So that's what he has done. So it is exponential at e to the power this value. So it just came out. So that's why this is just this.
Is calculus with respect to a vector, like hopefully you saw some of in Math 51 or some other place, not high school single variable calculus. On the other hand, to the extent you only half remember some of this stuff, most of the time you can just do perfectly well by thinking about what happens with one dimension at a time, and it generalizes the multivariable calculus. So if about all that you remember of calculus is that d dx of ax equals a, really it's the same thing that we're going to be using here, that here we have with the VC, well, at the end of the day, that's going to have terms of sort of 1 plus u0 component 2 plus so what we're going to be getting out is the u0 and u01 and the u02. So this will be all that is left with respect to VC1 when we take its derivative with respect to VC1, and this term will be the only thing left when we take the derivative with respect to the variable VC2. So the end result of with VC, so that's progress. So then at that point, we go on and we say, oh damn, we still have the denominator to, and that slightly more complex, but not so bad denominator. The one tool that we need to know and remember is how to use the chain rule. So the chain rule is when you're wanting to work out, so we have f of, so we want to say, okay, what we have here is we're working out a composition of function x, which is g of vc. Actually, maybe I shouldn't call it X. Whoops. Maybe I want to work out the chain rule. Well, what do? At that point, we have to actually remember something. We have to remember that the derivative of log is the 1 on X function. So this for Z, so that's then going to be 1 over the sum of W equals 1D multiplied by the derivative of sum. We want to say this VC variable to be using a different one.
Applying a chain rule, log is taking as f, and this is taking as a z set. So multiplication rule, f into differentiation of z plus z into differentiation of f. So write them.
Okay, so at that point, we're making some progress. Chain rule once more, VC. And so we then sort of repeat over. So we can move the derivative inside a sum always. So we're then taking the derivative of this. And so then the derivative of x is itself. So we're going to just have x of ux tvc times, this is sum of x equals 1 to v, times the derivative of ux tvc. Okay, and so then this is what we'd worked out before. We can just rewrite a ux. Okay, so we're now making progress. So if we start putting all of that together, what we have VC U0, numerator sum over x equals 1 to, then that was multiplied by our first term that came from the 1 on x, which gives you the sum of w equals 1 to v of the x of uw tvc. And this is where the fact that we changed the variables became important. And so by just sort of rewriting that a little, we can get that equals u0 minus the sum of v equals, x equals, right, x equals 1 to v of this x of x uwtvc times u of x. And so at that point, this sort of interesting thing has happened that we've ended up getting straight back exactly the softmax formula probability that we saw when we started. We can just rewrite that more conveniently as saying this equals u0 minus the sum over x equals 1 to v of the probability of x given c times ux. And so what we have at that moment is this thing here is an expectation. And so this is an average over all the context vectors weighted by their probability according to the model. And so it's always the case with these softmax style models that what you get out for the derivatives is you get the observed minus the expected. So our model is good if our model on average predicts exactly the word vector that we actually see. And so we're going to try and adjust the parameters of our model so it does that much as possible. Now, I mean, we try and make it do it as much as possible. I mean, of course, as you'll find, you can never get close, right? You know, if I just say to you, okay, the word is croissant, which words are going to occur in the context of croissant? I mean, you can't answer that. There are all sorts of sentences that you could say that involve the word croissant. So actually, our particular probability estimates are going to be kind of small. But nevertheless, we want to sort of fiddle our word vectors to try and make those estimates as high as we possibly can. So I've gone on about this stuff a bit, but haven't actually sort of shown you any of what actually happens. So I just want to quickly show you a bit of that as to what actually happens with word vectors. So here's a simple little IPython notebook, which is also what you'll be using for assignment 1 only. So in the first cell, I import a bunch of stuff. So we've got NumPy for our vectors, Matplotlib for plotting. It learns kind of your machine learning Swiss Army knife. GenSim is a package that you may well not have seen before. It's a package that's often used for word vectors. It's not really used for deep learning, so this is the only time you'll see it in the class. But if you just want a good package for working with word vectors and some other application, it's a good one to know about. Okay, so then in my second cell here, I'm loading a particular set of word vectors. So these are our glove word vectors that we made at Stanford in 2014. And I'm loading 100-dimensional word vectors so that things are a little bit quicker for me while I'm doing things here. I sort of do this model of bread and croissant. Well, what I've just got here is word vectors. So I just wanted to sort of show you that there are word vectors. Well, maybe I should have loaded those word vectors in advance. Let's see. Oh, okay, well, I'm in business. Okay, so, right, so here are my word vectors for bread and croissant. And while you can see that maybe these two words are a bit similar, so both of them are negative in the first dimension, positive in the second, negative in the third, positive in the fourth, negative in the fifth. So it sort of looks like they might have a fair bit of dot product, which is kind of what we want because bread and croissant are kind of similar. But what we can do is actually ask the model, and these are GenSim functions now, you know, what are the most similar words? So I can ask for croissant, what are the most similar words to that, and it will tell me it's things like brioche, baguette, focaccia. So that's pretty good. Pudding is perhaps a little bit more questionable. We can say most similar to the USA, and it says Canada, America, USA with periods, United States. That's pretty good. Most similar to banana. I get out coconuts, mangoes, bananas, sort of fairly tropical fruit. Great. Now, before finishing, though, I want to show you something slightly more than just similarity, which was one of the amazing things that people observed with these word vectors. And that was to say, you can actually sort of do arithmetic in this vector space that makes sense. And so in particular, people suggested this analogy task. And so the idea of the analogy task is you should be able to start with a word like king, and you should be able to subtract out a male component from it, add back in a woman component, and then you should be able to ask, well, what word is over here? And what you'd like is that the word over there is queen. And so this sort of little bit of, so we're going to do that with this sort of same most similar function, which is actually more. So as well as having positive words, you can ask for most similar negative words, and you might wonder what's most negatively similar to a banana, and you might be thinking, oh, it's, I don't know, some kind of meat or something. Actually, that by itself isn't very useful, because when you could just ask for most negatively similar to things, you tend to get crazy strings that were found in the data set that you don't know what they mean, if anything. But if we put the two together, we can use the most similar function with positives and negatives to do analogies. So we're going to say we want a positive king, we want to subtract out negatively man, we want to then add in positively woman and find out what's most similar to this point in the space. So my analogy function does that precisely that by taking a couple of most similar ones and then subtracting out the negative one. And so we can try out this analogy function. So I can do the analogy I show in the picture with man is to king as woman is, wait, sorry, I'm not saying this right. Yeah, man is to king as woman is to, oh, sorry, I haven't done my cells. Okay, man is the king as woman is the queen. So that's great, and that's works well. I mean, and you can do it the sort of other way around, king is to man as queen is to woman. If this only worked for that one freakish example, you maybe wouldn't be very impressed. But, you know, it actually turns out like it's not perfect, but you can do all sorts of fun analogies with this, and they actually work. So, you know, I could ask for something like an analogy here's a good one. Australia is to be as it comes out as champagne, which is pretty good. Or I could ask for something like Anamara is to. When I have to point out that this data was and model was built in 2014, so you can't ask anything about Donald Trump in it. Well, you can. Trump is in there, but not as president. But I could ask something like analogy is to what, and you can think of what you think is the right analogy there. The analogy it returns is Nixon. So I guess that depends on what you think of Bill Clinton as to whether you think that was a good analogy or not. You can also do sort of linguistic analogies with it. So you can do something like analogy, tall is to tallest as long is to what, and it does longest. So it really does sort of knows a lot about the meaning and behavior of words. And, I think when these methods were first developed, and hopefully still for you, that people were just gobsmacked about how well this actually worked at capturing enough words. And so these word vectors then went everywhere as a new representation that was so powerful for working out word meaning. And so that's our starting point for this class, and we'll say a bit more about them next time, and they're also the basis of what you're looking at for the first assignment.
Could I ask a quick question about the distinction between the two vectors per word?
Yes.
So my understanding is that there can be several context words per word in the vocabulary, like word in the vocabulary. But then if there's only two vectors, I thought the distinction between the two is that one's like the actual word and one's like the context word. But if there are multiple context words,
right,
how do you pick just two then?
Well, so we're doing every one of them, right? So like. Maybe I won't turn back on the screen share, but we were doing in the objective function there was a sum over. So you've got this big corpus of text, right? So you're taking a sum over every word, which is it appearing as the center word, and then inside that there's a second sum, which is for each word in the context. So you are going to count each word as a context word, and so then for one particular term of that objective function, you've got a particular context word and a particular center word, but you're then sort of summing over different context words for each center word, and then you're summing over all of the decisions of different center words. And to say just a sentence more about having two vectors, I mean, in some sense it's an ugly detail, but it was done to make things sort of simple and fast. So, if you look at the math carefully, if you sort of treated the two vectors as the same. So if you use the same vectors for center and context, and you say, okay, let's work out the derivatives, things get uglier. And the reason that they get uglier is it's okay, when I'm iterating over all the choices of context word, oh my God, sometimes the context word is going to be the same as the center word. And so that messes with working out my derivatives. Whereas by taking them as separate vectors, that never happens. So it's easy. But the kind of interesting thing is, saying that you have these two different representations sort of just ends up really sort of doing no harm. And my wave my hands argument for that is, since we're kind of moving through each position in the corpus one by one, a word that is the center word at one moment is going to be the context word at the next moment. And the word that was the context word is going to have become the center word. So you're sort of doing the computation both ways in each case. And so you should be able to convince yourself that the two representations for the word end up being very similar. And they do. Not identical for technical reasons at ends of documents and things like that, but very, very similar. And so effectively, you tend to get two very similar representations for each word, and we just average them and call that the word vector. And so when we use word vectors, we just have one vector for each word.
That makes sense. Thank you.
I have a question purely out of curiosity. So we saw that when we projected the vectors, the word vectors onto the 2D surface, we saw like little clusters of words that are similar to each other. And then later on, we saw that with the analogies thing, we kind of see that there's these directional vectors that sort of indicate like the ruler of or the CEO of, something like that. And so I'm wondering, are there relationships between those relational vectors themselves, such as like, is the ruler of vector sort of similar to the CEO of vector, which is very different from like makes a good sandwich with vector? Is there any research on that?
That's a good question. Well, you stumped me already in the first lecture. I can't actually think of a piece of research, and so I'm not sure I have a confident answer. I mean, it seems like that's a really easy thing to check, one vector for each word.
That makes sense. Thank you.
I have a question purely out of curiosity. So we saw that when we projected the vectors, the word vectors onto the 2D surface, we saw like little clusters of words that are similar to each other. And then later on, we saw that with the analogies thing, we kind of see that there's these directional vectors that sort of indicate like the ruler of or the CEO of, something like that. And so I'm wondering, are there relationships between those relational vectors themselves, such as like, is the ruler of vector sort of similar to the CEO of vector, which is very different from like is makes a good sandwich with vector? Is there any research on that?
That's a good question. Well, you stumped me already in the first lecture. I mean, I can't actually think of a piece of research, and so I'm not sure I have a confident answer. I mean, it seems like that's a really easy thing to check once you have one of these sets of word vectors, that it seems like for any relationship that is represented well enough by a word, you should be able to see if it comes out.
Okay, so it looks like what he's asking is one he told is male and female based on the gender. That analogy thing works for something related to what he did Obama is to Clinton is to, so for that it works. So can we check for things, let's say, I mean, what pencil is to book or pencil is to writing is to water bottle is to drinking. So that analogy, right, in terms of thing is to action word, does the corpus works for that or not? So there can be different analogies. So these sort of different analogies, right, is the word whatever we have built the model, right, works on it. So that's what he's asking.
Kind of similar. I mean, I'm not sure. We can look and see.
Yeah, that's totally okay. Just curious.
Sorry, I missed the last little bit to your answer to first question. So when you wanted to collapse two vectors for the same word, did you say you usually take the average?
Different people have done different things, but the most common practice is after you've, there's still a bit more I have to cover about running word2vec that we didn't really get through today, so I've still got a bit more work to do on Thursday. But once you run your word2vec algorithm and you sort of, your output is two vectors for each word, and kind of when it's center and when it's context. And so typically people just average those two vectors and say, okay, that's the representation of the word croissant, and that's what appears in the sort of word vectors file like the one I loaded.
That makes sense. Thank you.
Thanks. So my question is, if a word have two different meanings or multiple different meanings, can we still represent it as a same single vector?
Yes, that's a very good question. And actually, there is some content on that in Thursday's lecture, so I can say that's a very
meanings. Can we still? Thanks. So my question is, if a word have two different meanings or multiple different meanings, can we still represent it as a same single vector?
Yes, that's a very good question. And actually, there is some content on that in Thursday's lecture, so I can say more about that. But yeah, the first reaction is you kind of should be scared, because something I've said nothing about at all is, most words, especially short common words, have lots of meaning. So if you have a word like star, that can be astronomical object, or it can be, a film star, a Hollywood star, or it can be something like the gold stars that you got in elementary school. And we're just taking all those uses of the word star and collapsing them together into one word vector. And you might think that's really crazy and bad, but actually turns out to work rather well. Maybe I won't go through all of that right now, because there is actually stuff on that on Thursday's lecture.
Oh, I see. Thanks.
You can look ahead at the slides for next time. Oh, wait.
I had a quick question. I know this might seem kind of strange to ask, but I guess a lot of us were also taking this course because of the hype between AI and speech recognition. And my basic question, maybe too basic, is do we look at how to implement, or do we look at like the stack of like something like Alexa or something for like speech to context actions in this course, or is it just primarily understanding?
So this is an unusual quarter, but for this quarter, there's a very clear answer, which is this quarter, there's also a speech class being taught, which is CS224S, a speech class being taught by Andrew Maas. And, this is a class that's been more irregularly offered. Sometimes it's only been offered every third year, but it's being offered right now. So if what you want to do is learn about speech recognition and learn about sort of methods for building dialogue systems, you should do CS224S. So, for this class in general, the vast bulk of this class is working with, like some of the ones I mentioned. We do machine translation. We do other years that seem a little bit silly.
I guess I'm fine with, but I guess you're
I'm now getting a bad echo. I'm not sure if that's my fault or your fault, but mix of stuff. So, the sort of pure speech problems classically have been doing speech recognition, so going from a speech signal to text, and doing text to speech, going from text to a speech signal. And both of those are problems which are now normally done, including by the cell phone that sits in your pocket, using neural networks. And so it covers both of those. But then between that, the class covers quite a bit. And in particular, it starts off with looking at building dialogue systems. So this is sort of something like Alexa, Google Assistant, Siri, and you do dialogues.
I think there was some people in the chat noticing that the opposites were really near to each other, which was kind of odd. But I was also wondering, what about like positive and negative valence or like affect? Is that captured well in this type of model, or is it like not captured well? Like with the opposites, how those weren't really.
Yeah. So the short answer is for both of those, and so this is a good question, a good observation. The short answer is no, both of those are captured really, really badly. There's a definition. When I say really, really badly, what I mean is, if that's what you want to focus on, you've got problems. It's not that the algorithm doesn't work. So precisely what you find is that, antonyms generally occur in very similar topics, because, whether it's saying, John is really tall or John is really short, or that movie was fantastic or that movie was terrible, right? You get antonyms occurring in the same context. So because of that, their vectors are very similar. And similarly for sort of affect and sentiment-based words, well, like my great and terrible example, their contexts are similar. Therefore, that if you're just learning this kind of predict words in context models, that no, that's not captured. Now, that's not the end of the story. Absolutely, people wanted to use neural networks for sentiment and other kinds of sort of connotation affect, and there are very good ways of doing that. But somehow you have to do something more than simply predicting words in context, because that's not sufficient to capture that dimension. More on that later. Predicting words and models that no, that's not captured. Now, that's not the end of the story. Absolutely, people wanted to use neural networks for sentiment and other kinds of sort of connotation affect, and there are very good ways of doing that. But somehow you have to do something more than simply predicting words in context, because that's not sufficient to capture that dimension. More on that later.
Does this happen to like adjectives too, like very basic adjectives like so and like not? Because those would like appear in like similar contexts, right?
What was your first example before not?
Like so. This is so cool.
Yeah. So that's actually a good question as well. So yeah, so there are these very common words that are commonly referred to as function words by linguists, which includes ones like so and not, but other ones like and prepositions like to and on. You sort of might suspect that the word vectors for those don't work out very well, because they occur in all kinds of different contexts and they're not very distinct from each other in many cases. And to a first approximation, I think that's true. And part of why I didn't use those as examples in my slides. Yeah. But, at the end of the day, we do build up vector representations of those words too. And you'll see in a few lectures' time, when we start building what we call language models, that actually they do a great job in those words as well. To explain what I'm meaning there, another feature of the word-to-vec model is that actually ignore the position of words, right? So it said, I'm going to predict every word around the center word, but, I'm predicting it in the same way. I'm not predicting differently the word before me versus the word after me, or the word to away in either direction, right? They're all just predicted the same by that one probability function. And so if that's all you've got, that sort of destroys your ability to do a good job at capturing these sort of common, more grammatical words like so, not, and. But we build slightly different models that are more sensitive to the structure of sentences, and then we
So one issue with this, he told that usually the words that are opposite to each other, means Abhishek is tall, Priya is short. Usually the opposite words, right? what words come near them, right, are mostly similar. So that's why you will see at least he's saying that in this model, right, they will come nearby. So that's one problem in this. The second he told us, um, we just look at the context. It doesn't matter for this right here, if for with right, NLP is closer or CS224N is closer, or here as well, it with deep. Uh, Deep is closer to with, and then learning is a bit more farther. As of now, we just take deep learning as it is. It doesn't matter if deep is much more closer to it and learning is much more closer to. So that bit of information is also not getting stored here. Sorry, I'm typing.
Start doing a good job on those too.
Okay, thank you.
I had a question about the characterization of word to vec. Because I read well research in Medium, and they seem to characterize architecture as more of a skip gram model, which was slightly different from how it was presented in the right? So are these like two complementary ways of looking at it, or?
Yeah. So I've still got more to say, so stay tuned Thursday for more kind of a framework for building word vectors, and that there are sort of several variant precise algorithms within the framework. And one of them is whether you're predicting the context words or whether you're predicting the center word. So the model I showed was predicting the context words, so it was the skipgram model. But then there's sort of a detail of how in particular do you do the optimization. And what I presented was the sort of easiest way to do it, which is naive optimization with the equation, the softmax equation for word vectors. It turns out that naive optimization is sort of needlessly expensive, and people have come up with faster ways of doing it. In particular, the commonest thing you see is what's called skipgram with negative sampling, and the negative sampling is then sort of a much more efficient way to estimate things, and I'll mention that on Thursday.
Right. Okay. Thank you.
Who's asking for more information about how word vectors are constructed beyond the summary of random initialization and then gradient-based iterative optimization?
Yeah. So I sort of will do a bit more connecting this together in the Thursday lecture. I guess there's sort of only so much one can fit in the first class. But the picture is essentially the picture I showed the pieces of. So to learn word vectors, you start off by having a vector for each word type, both for context and outside, and those vectors you initialize randomly. So that you just put small little numbers that are randomly generated in each vector component, and that's just your starting point. And so from there on, you're using an iterative algorithm where you're progressively updating those word vectors so they do a better job at predicting which words appear in the context of other words. And the way that we're going to do that is by using the gradients that I was sort of starting to show how to calculate. And then, once you have a gradient, you can walk in the opposite direction of the gradient, and you're then walking downhill, i.e. you're minimizing your loss. And we're going to sort of do lots of that until our word vectors get as good as possible. So, it's really all math, but in some sense, word vector learning is sort of miraculous, since you do literally just start off with completely random word vectors and run this algorithm of predicting words for a long time, and out of nothing emerges these word vectors that represent meaning well.
Thanks, everyone. We will also try to see what all assignments and everything are in here that they have put in. So for the time being, thanks.